welcome back to Next Gen Manufacturing Nexus. This is where we get into the nitty-gritty of the tech that's literally building the world of tomorrow. And today, oh man, we're diving deep into a process that might just change everything about how we build airplanes.
So have you ever really stopped to think about how we build something like this? I mean, look at it. A single wind turbine blade can be 250 feet long. It's a marvel of engineering. Making something that gigantic, that precise out of high-tech materials, that's a huge challenge. But the way they do it, well, that's where things get really interesting. Okay, so stick with me here. What if you could take the exact same technology used for those massive blades and use it to build an airplane? You're taking a proven tech from one industry and dropping it into aerospace. I mean, that's one of the toughest, most demanding fields out there. And believe me, that's the big question engineers are obsessed with right now.
And here it is. The technology that could make it all happen is called VARTM. And let me tell you, this isn't just a small tweak. We're talking about a process that could make aircraft parts cheaper, faster, and way, way bigger than we can today. This is a full-blown manufacturing revolution just waiting to happen.
All right, but before we go any further, to really get why VARTM is such a game changer, you have to understand the problem it's designed to fix. So let's talk about the big headache in aerospace manufacturing. I mean, think about it. Why is it so incredibly hard and expensive to build a modern airplane? We see them all the time, right? But the engineering that goes into making them lighter, stronger, and more fuel efficient, it's just mind-boggling. And the secret, the real challenge, it all boils down to one thing: the materials they're made of.
And that answer is advanced composite materials. We're talking about things like carbon fiber. This stuff is amazing. It's super strong and ridiculously lightweight. It's pretty much the dream material for an airplane, right? You get better performance, you burn less fuel. It's perfect. Except there's always a catch. And here's the catch. To get these composites to be so strong, you have to bake them, but not in your kitchen oven. We're talking about massive, high-pressure ovens called autoclaves. Seriously, picture a giant industrial pressure cooker. These things are the villain of our story. They cost a fortune, they eat up a ridiculous amount of energy, and this is the big one, the size of your oven literally limits the size of the part you can build. They are, without a doubt, the single biggest bottleneck in the entire process. So, if the autoclave is the villain, well, this is where our hero makes its grand entrance. What if you could get that same aerospace-grade quality, that same incredible strength, but you could just get rid of the oven completely? That's the promise of VARTM, manufacturing out of the oven.
Okay, so what is vacuum RTM? It stands for Vacuum-Assisted Resin Transfer Molding. It's a bit of a mouthful, I know, but the only part you really need to remember is Out of Autoclave, or OA for short. It's a totally different way of thinking about how to make these super important parts. So here's the core idea, and it's actually pretty brilliant. Instead of pressure cooking the part, you start with layers of dry fiber cloth. Think of it like a sponge. Then you use a vacuum to literally pull liquid resin all the way through it. The vacuum does all the hard work. It pulls the resin in and it squeezes all the layers together tight. Then the whole thing just hardens at room temperature or with a little bit of heat. No giant oven needed. Okay, that's the theory, right? Sounds cool, but what does this actually look like in a real factory? Let's go step by step through the industrial playbook for building a part with VARTM. It really boils down to 5 main stages. First, you've got stacking, then debulking, which is just squishing out the air. Then comes the magic part, infusion. After that, curing, where it all hardens. And finally, trimming and inspection to make sure it's perfect. Let's zoom in on that first step, stacking. This is so cool. When you're building a part for an airplane, you can't just wing it. So they use lasers that project the exact outline right onto the mold. It tells the technicians exactly where every single piece of fiber needs to go. We're talking about incredible precision to guarantee the final part is flawless. And here it is. This is the moment where the magic happens, the infusion. So once all those fiber layers are down, the entire thing gets sealed up under a giant plastic bag, a vacuum bag. You can see the little tubes going in. When they flip the switch and pull the vacuum, the air pressure outside the bag literally pushes that liquid resin through every nook and cranny of the part. It's amazing to watch it just flow through and soak into every single fiber. Okay. The process is clever, for sure, but does it make sense financially? Is it actually practical? This is where we have to look at the numbers. Let's talk about the big 3: cost, quality, and scale. So let's put them head to head.
Right off the bat, with VARTM, you're not running a giant, power-hungry oven, so your energy costs plummet. And because you don't have an oven, you're not limited by its size anymore. You can suddenly build massive, single-piece parts. We're talking an entire wing skin in one go. That's a huge deal for strength and weight. Now, what's the catch? Well, the special resins and materials for VARTM can be a bit more expensive up front.
And you can't talk about aerospace without talking about quality. This is absolutely non-negotiable. After a part is made, it has to be scanned for any tiny, hidden flaws using something called non-destructive testing, or NDT. And let me tell you, that gear is not cheap. Just look at this. An automated machine can run you €1 million. It's a really important reality check. Even though you save a ton of money by ditching the autoclave, you still have to invest heavily to make sure every single part is safe enough to fly.
And that brings us to the bottom line, the key economic principle here. This quote from Ferreira's research nails it. Basically, it all comes down to scale. If you're only making a handful of parts, VARTM might actually be more expensive. But the moment you start to increase your production rate, those massive savings from not having an autoclave kick in, and suddenly, VARTM isn't just an option, it's the smartest financial choice.
So we've got a clever process, we've got a business case that works when you scale up. So what's next? What does the future actually look like for VARTM? Up in the air.
This slide says it all, really. On one side, you have the wind industry, where VART is already king. It's proven, it's reliable, it's industrialized. On the other side, you have aerospace. The tech is ready. We know it works. The real question is, can it clear the bar for an industry where the stakes are, astronomically higher?
And trust me, it is not an easy jump to make. The hurdles in aerospace are just on another level. The tolerances for error are practically zero. The safety testing is beyond rigorous. And you have to prove that these new materials and processes are just as good or better than what's been used for decades. Oh, and yeah, it also has to compete against the really, really advanced automated systems that are already out there.
So that leaves us with one big final question. We know VARTM can build some of the biggest composite structures on the planet. We know it promises a future that's cheaper, faster, and lets us build things we could only dream of before. So, will the next generation of aircraft be built without ovens? Will they be born from a vacuum instead of a furnace? The race to figure that out is officially on.